So today I learned how to use BinPackCollator in LLM Foundry, which seems to be LLM Foundry's built-in sequence packing method. So this is going to be a short video, a today I learned type of video, so it's a little more disorganized as I'm just walking through something that I just learned and haven't really fleshed out yet fully. So the first thing I was doing was I just Googled for LLM Foundry sequence packing and got this hit. And if you go to LLM Foundry data packing.py, they have something called BinPackCollator. Now, looking at it, it's not immediately clear that it's doing packing. So, I didn't exactly understand. I didn't read this and I was like, "Oh yeah, this makes sense." But, the docstring is very promising. Utility collator for packing to reduce padding. So I'm like, "Okay, let's see if this works." So a couple different files, I was searching around in the code base. I found it here in their utils file. There's a get fine tuning collator and BinPackCollator appears there, and it wraps itself in loss generating tokens collator wrapper. Then there's the data fine tuning data loader.py, and it has this packing ratio which it gets from the dataset config, which comes from the train YAML. And packing ratio is auto, then it does this auto packing. It's 1, then it returns the collate function, and then if it's greater than 1, then it returns a BinPackCollator as the collate function. And then if you scroll down here to look at the script, it has this build fine-tune data loader that it calls. So yeah, it was interesting to see. I'm like, okay, this is, more information. And then if you look at the actual training script, so this is LLM Foundry command utils train.py, they have the train loader, which is using build train loader, and it passes to it the train loader config. And the train loader config, as an example, is this section of your YAML. So here's the train loader config comes out of that YAML part. And then if you look at LLM Foundry data loader, where build data loader is defined, it pops out from the training config. It builds a data loader from a config, and it pops out the name. And then from registry, it passes that name. And that name, in this case, is the string fine tuning. So these were the different hits after searching the code base where I was starting to kind of piece together. I'm like, okay, I don't really understand exactly how this construct from registry works. I don't really understand this concept of registry in LLM Foundry, but there seems to be this fine-tuning name. There's a build fine-tuning data loader, and then there's this packing ratio where if you pass that value, it kind of triggers the usage of this BinPackCollator. So this was, pieces that I had put together, and I fed Claude LLM Foundry as project knowledge, and I selected, those relevant folders like data, command utils, etc. And it was using that GitHub project knowledge feature. And I just asked it, hey, I want to figure out how to use BinPackCollator. I'm not sure how or where to call it or set it up so that the data loader uses it. Let me look at this thoroughly and let me know if you can give me pointers. And it was actually in this conversation with Claude that it pointed out, this importance of the name being fine-tuning and this packing ratio. This is where I learned about this packing ratio. And then later, I looked it up in one of these. Yeah, I forget which one, but yeah, one of these where it was using it. And so it's like, yeah, this has to be either a float value or auto. How it works is that the build fine-tuning data loader function detects the packing ratio parameter. It calls build collate function, which creates a BinPackCollator instance. It wraps around the base collator, and it packs multiple examples into batch item, reducing padding waste. So if there's a device batch size of 4 and a packing ratio of 5, it'll pack 20 raw examples per batch. And then, there's some additional notes. So there's this profile packing, which I think is what's triggered when you use auto packing, and yeah, some other items like that. And let me just make sure there's nothing else. Yeah, and this is where Claude was explaining that the name from the config is extracted here, and that's what triggers this whole fine-tuning data loader packing ratio logic. So I think that's it, everything that I want to show here. So that was a great start. I felt really good that this was promising, but I don't really understand it, and I have to actually see what the data looks like. So at this point now, this is now the third or fourth time I've needed to write a composer callback, and this time I wrote it pretty much myself. I referenced the last loss inspector composer callback that I created and basically gutted all the functions that I didn't need and kind of built up the main event handler that I needed. So this is what it looks like. I'm calling it data inspector, and it inherits from the callback class from composer. And I'm using modal, so I have this volume where I'm going to have a BinPackCollator folder, and that's where it's going to save this log. And for the log, I just have a dictionary. I'm just going to save it as a JSON file. So the first thing I did was I created these helper functions. So there's _save. It makes the JSON file, or the JSON, or the bin, what is it called? BinPackCollator folder. And then it creates a log file, a path called dataInspectorLogs.json. And then it dumps the log into that. So it basically overwrites it every time I run this training command. And then key item here is that you have to append your callback to the callbacks list, and then that gets passed to the composer trainer as the callbacks parameter. So that was the first thing I did, is make a save function and make sure that it actually saves something. And then the key thing here is the log function, and this is where the actual logging takes place. And along with the normal state parameter that this takes, that all these event handlers take. I actually probably could have gotten rid of that, but it takes an event name, it takes the batch number, and it takes a list of values. And the list of values, this is actually incorrect. This should be, it's a list of tuples of strings. And so I iterate through my list of tuples, and I destructure my label and value strings. And then to my log, which is just a dictionary, I'm creating a new key, which is event name _ batch number _ label, and I'm storing as the value whatever the value is in this list of tuples. So I iterate through that list, I save each label value pair, and then I hit self._save, so it dumps that log into the JSON file. So that was my first couple iterations. I just passed different values for event name, batch number, values, and make sure this worked. And then here's the main star of the show. So this is the after data loader function. Maybe there's other events that I'm going to use or handle in this case, but I thought that the after data loader was a good place to inject this callback. So it takes the state, which is really important, as everything is based on that. It's going to log the after data loader string. It's going to log as batch number. It's going to log state.timestamp.batch.value. And then it's going to log, 6 different things. So from the top, I wanted to make sure that the collate function is in fact the collate function that I'm expecting it to be, which is the BinPackCollator. So I grab the data loader from the state, and then the data loader has a collate function method. And this method here, if we go back, is loss generating tokens collator wrapper. And then that has a base collator attribute, which is the actual kind of specific collator function that's being used. Then I also printed out the input ID's shape. So I access the batch, I access the input IDs, and I print the shape. The total number of tokens is the second value of the shape, so I'm printing that out. And then these two are the main things here. This is going to let me know if the sequence packing is actually working. So first I print out the number of padding tokens. So I iterate through the input IDs for the first item in the batch. And if the item is 0, then I add it to this list, and I take the length of that list. I guess I could have done also like a sum of that, true, false, or something. And then for non-padding tokens, it's the opposite. So if the item in input IDs, the token tensor item, is not 0, then it's a non-padding token. And this is because the small LM2 135 million tokenizer end of sequence token ID, which is used as the padding token, is 0. If you had a different tokenizer, this would be whatever your EOS token ID is. And then I always like to look at all of the input IDs, so you have to convert it to a list because otherwise it'll print out that abbreviated tensor that PyTorch does. So you convert it to a list, convert that to a string, and that's what it's printing out. So for each of these tuples in this list, it's going to iterate through, grab the label and value, and store that in the log, and then save the log. So relatively straightforward, right? This was much simpler than tracking weight data types, gradient data types that I've done before. So this was a lot easier to work with. So where does this go? This goes right in train.py, and it goes right before you define your trainer, and you make sure you append it to callbacks. Then in my modal script, I save that train.py and basically overwrite the existing train.py. And then train YAML file where I have pretty much standard things that are in the LLM Foundry examples. But under train loader, I make sure that this is fine tuning. And then under it, I put a packing ratio attribute that has a greater than 1.0 value. So this means that it's going to kick in the packing ratio. So that's great. I run that, and this is the output I got with the BinPackCollator. So here's the collate function, and here is confirmation that it's using the expected collate function, which is BinPackCollator. The number of items in the batch is 4, and each one is 2048 tokens long. The total number of tokens is 2048. That's just the second shape item. And here is the main thing. The number of padding tokens is 102. The number of non-padding tokens is 1946. So that was super important to see. When I ran this without packing ratio specified in the train YAML, these numbers were basically flipped. It was about 1,800 or so padding tokens and only about 200 or something non-padding tokens. So basically it flips the entire ratio, and you go from 90% padding tokens to 5% padding tokens. And this also resulted in a drop in loss. And let me see if I can open that up here. So here was the packing ratio lost. It was about 0.98. And the no packing, so without packing ratio, it was about 1.05, 1.1 or so. So, somewhere around like a 5-6% drop in loss. And then just inspecting the input IDs, because it's always nice to just confirm that, yeah, there's definitely lots and lots of non-zero tokens. And then if we look at it down here, we can see that we have a bunch of padding tokens at the end. And so, yeah, overall, this felt really good. I think one more thing that I would like to do, which I haven't done yet, is put in a line. So going back to my callback, custom callback, I think one more thing I want to do is I want to add a decoded tokenizer situation. So I wasn't planning on making this a live coding video. So I'm going to give it one attempt, and if it doesn't work, I'm going to just put it in my blog post that I'll probably post tomorrow. But it'll be something like this, where I'll just decoded tokens, and then this is going to be tough to do from memory, but let me see. I'm going to go here. So I guess we're doing this live. And let's see. I have a composer callback that I think uses tokenizer. Why is that not working? Okay. Let's look at this one. All right, so state.model is something I can access. And state.model again. All right, let's just give this a try. So let's see if I can do state.model.tokenizer. So let's see if I can just access the tokenizer to begin with. All right, so I'm going to run this, but what I'm hoping is that this does show the tokenizer, and then once it shows the tokenizer, I can then decode it, and then we can look at the actual decoded tokens. Okay, great. So if we look at decoded tokens, here is our tokenizer. So that is an excellent start. So now what we can do is we can do .decode, and we're going to pass it the first item. So I'm just going to pass it state.batch, input IDs 0, and I think this should decode it correctly. So save that and run it again. Okay, so looking at it here, we have decoded tokens, and then we have, this is the MetaMath QA dataset. So he buys 12 red lights, blah, blah, blah. And actually, let's do this. Let's search for end of text. All right, here we go. So we can see the first end of text is here. The next one is here. So we can see that these are indeed truly sequence packed items. And then we get to our padding tokens at the end. So if we look at the sequence or the end of sequence tokens or end of stream tokens, we have 1, sequence 2, 3, 4, 5, 6, 7, 8. So we actually have 8 different sequences packed into here. And so, yeah, that's more than what I would expect. So the packing ratio doesn't seem to be strict. So I had a packing ratio of 5.0 and my batch size is 4, so I would expect 20. But I guess this is how much fits, given whatever calculation is happening. So, we still have some space left, but, probably not enough to add in another sequence. And then going back here, I just added this R, so it said model.tokenize.decode, so I added model.tokenizer.decode. But that's it. I think that is enough for me to say that even though I don't understand how LLM Foundry's sequence packer works, I can see that it is working. And it's working because of 2 things. Number 1, I have the fine-tuning name for the train loader. And number 2, I have a packing ratio greater than 1.0 defined. And so now that means, we can test different packing ratio values, etc. But the coolest thing is that now we are not wasting 90% of every batch with padding tokens, which is just an insane concept to me. Now we are utilizing 90% of the batch. So this will end up in faster training, hopefully faster convergence, all that good stuff, faster iteration, faster experiments, and faster results. So super excited. I'm very happy that the live coding experience went well. I will probably be posting this as a blog post tomorrow, but we'll see how that goes. But anyways, thank you for watching. Please like, subscribe, comment, etc. And I will see you in the next video.